Hi everyone, today we're covering 2.2, intramolecular force and potential energy. Now, as a reminder from the last video, we're mostly going to talk about covalent bonds now. Covalent bonds share electrons between nuclei. They can be nonpolar, in other words, they're shared equally, or they can be polar, where they're shared unequally. You can classify them as single, double, or triple bonds, or an average of those based on what we call resonance. And we're going to cover this a lot more in topic 2.6, so we don't have to worry about that quite yet. The biggest goal that we're going to talk about here is low energy. We always want to lower the amount of energy possible. And so we'll talk about that first by just discussing bond strength. And we've talked about it a little bit in terms of enthalpy, but strength of covalent bonds really depends only on the overlap between valence orbitals of the bonded atoms. And so remember, our valence orbitals are, for example, like a p orbital, right? This would be one p orbital. And so if I have, let's say, O2, which typically looks like this, my O coming out of the nucleus would have a p orbital with an electron there. My other O would have a p orbital here. We want good overlap between these two orbitals to get a good bond. So there are four trends that we typically see here. Bonds between hydrogen and atoms in the same column of the periodic table decrease in strength as we go down. So what this means is HF, for example, has a stronger bond than HI. HC has a stronger bond than HSI. Bonds between similar or like atoms usually become weaker as you go down. So a carbon-carbon bond is going to be stronger than a silicon-silicon bond, which is going to be stronger than a germanium-germanium bond. There are some exceptions. Don't worry about the exceptions. Just focus on the trend. The third trend is that elements in period 3 and 4 rarely form multiple bonds with themselves. So if we look down at period 3, these are things like, arsenic, As, or bromine, for example, is also in period 4. Things in period 4 and period 3 generally don't make multiple bonds with themselves. Things like sulfur, phosphorus, all of those. Multiple bonds between carbon, oxygen, or nitrogen and a period 3 element such as phosphorus and sulfur tend to be unusually strong as well. And so, for example, PO is really strong, right? Oxygen, as well as P, which is a third period element. This is a really, really, really strong bond. It's almost impossible to break apart. So those are going to be really strong. P double bond N, for example, is pretty strong. S double bond O is really strong. And so that's the last trend that we generally see here. And one way that we can look at this potential energy is by graphing it. And so what we have here is energy. On the top, we have repulsion. And here in the negative, we have attraction. And generally, we want to maximize attraction. And so if we plot the amount of energy versus the distance between the two nuclei, right, the nucleus, or in other words, where all the protons are, we see this trend. If they're too close to each other, in other words, the H's are basically on top of each other, that's way too much energy. They just want to repel. The energy will decrease until you reach what we call the Goldilocks zone. That's right here, where it's just right. Recall, the story of Goldilocks. It's just right at that particular moment. But then if you start putting them too far away from each other, you get to the point where they don't want to bond anymore. And so suddenly they're too far. And so for every single bond, we have this good distance right here where the two nuclei are not too close and they're not too far. They're in just the right zone to actually form a bond. And that length that they form that bond, or at least where the attraction is highest, that is your bond length. So we've discussed this a little bit, but this difference here from 0 all the way down to that lowest point, that's the energy necessary to break the bonds between the atoms. In other words, the bond dissociation energy, which we've discussed before. We've talked about this. Another term of this is bond enthalpy. So that energy from the 0 to where you get that sweet spot where it really actually wants to bond, that amount of energy is required to actually break it. So for example, if down to this part, if this is 137 kilojoules per mole, just as an example, you would need at least 137 kilojoules per mole to break this bond apart. Another thing that strengthens bonding is bond order. And so the bond order is the number of bonding pairs of electrons between two atoms. And so for our most standard case we see here is single bonds. In a single bond, we have 2 electrons. It's denoted as just a line between the 2 atoms. You call that bond order 1. It's the weakest of them because it's only 1 bond, and it has the longest bond length. Generally, long bond length equals weak bond, which makes sense. If they're far away from each other, they're not going to want to bond. The next bond type is double. This has 4 electrons in it, so it's double a single bond. We put 2 lines in between our 2 atoms. We say that's a second bond order. It has a little bit more strength, and the length is slightly shorter than that of a single bond. And finally, in a triple bond, we denote that as 3 lines between the atoms. Its order is 3, and it's the strongest bond with the shortest length. And so, for example, if I take CC versus C double bond C versus C triple bond C, this is going to be strongest and closest to each other. Now, for ionic bonds, we've actually already discussed this before, but I'm just going to remind us, it goes based off of Coulomb's law. In other words, the energy is proportional to the charge of one ion versus the charge of the other ion over the distance squared, where Q equals charge and R equals bonding radius. And so the higher the charge, the stronger the bond, and the closer they are to each other, the stronger the force of attraction. In other words, the stronger the bond. Generally, the stronger force of attraction also leads to a higher melting point. That's all for this video. Thanks, guys.